Okay, we're at the top of page 12 in your review notes and continuing with intermolecular attractions. All right, and the next intermolecular attraction or force of attraction is the molecule-ion attractions. And this comes up whenever you have a salt dissolved in water, giving you an aqueous solution. So an example would be like NaCl, AQ. But there are many other examples of any ionic compound in water should give you this. All right. So in this case, what's going to happen is the reason why the water is able to dissolve the salt, come in between the crystal, and separate the ions from each other is because the water is attracted to the ions just as the ions are attracted to the water. If you recall, the water is a polar molecule, which we could depict like this, this oval with a negative and a positive pole. It's also known as a dipole because of that. And so what happens is that the negative pole of the water molecule, which is the oxygen atom, will be attracted to the sodium ions, which are positive. And for that matter, the chloride ions would be attracted to the positive pole. We could draw that like this, with dashed lines represented the attractions. Because if you recall, the hydrogen is the positive pole. So these attractions are called molecule-ion attractions because it's the attraction between a molecule and an ion. All right, and that anytime you have hydrated ions, meaning ions surrounded by water, this would be an Na plus AQ. And of course you would have more than one water molecule surrounding the sodium ion to keep it separated from the chloride ion in solution. And this would be the Cl minus AQ. And so we speak about these in the solutions unit, and we call them hydrated ions. We'll talk more about that later. All right, let's continue to the last attraction, because you probably were wondering, well, we have attractions between polar molecules, which are the dipole-dipoles. We have the very strong dipole attractions known as hydrogen bonding. We have these molecule-ion attractions. And now let's turn our attention to the attractions between non-dipoles. The so-called London dispersion forces, or the van der Waals forces. Now, it's possible this may not have been covered in your class, but you should certainly be aware of them. You don't have to really know how they are caused or the dynamics that's going on here. I'll explain it, but you should know some pointers, some applications of this. All right. So first of all, the attraction between two non-dipoles. Remember, any of those molecules on the non-polar side of your top sixes, the CO2, the CH4, or any of the Hankel-Briffs, the attractions between them would be just that, dispersion forces. Now, how do we explain them? Because remember, to represent a non-dipole means it does not have a positive and a negative pole. We would write the positive and the negative in the center of this oval, indicating that it cancels out. There's an even distribution of charge, and so there's no positive or negative side, and therefore it shouldn't stick. So if we leave it just like that, there should be no stick, no force of attraction between these molecules. So what happens is the following. What's proposed is that one of these molecules ends up turning, by chance, first of all, into a dipole. And that's certainly possible because this positive and negative thing really has to do with the motion of electrons. And it is possible for there to be more electrons on one side of the molecule than the other for a moment in time. And so momentarily, that molecule turns into a dipole. Now, what happens from that point is that this molecule will induce the same thing in a neighboring molecule. So we'll call this thing here induction. How one charged object affects the distribution of charges in another charged object. So the negative here is going to repel any negative here to the opposite side. And so one molecule turning into a dipole forces another molecule to turn into a dipole. So that would be the second thing. And finally, the third that happens. And now, momentarily, what we have is some induced dipoles. And there'll be an attraction between them, between the positive pole here that was induced and the negative here. And so dispersion forces are momentary induced dipole-dipole attraction. Just from the way it's described, you can tell that these are the weakest of the intermolecular forces. When does this come up? Well, it comes up in questions dealing with boiling point. If you consider the molecules in group 17, that is fluorine molecules and chlorine molecules and bromine molecules and iodine molecules, as you go down this group, since the size of the molecules increases, since we have more and more electrons going from 9 to 17 to bromine 35 to iodine 53, the more electrons are involved in this process, this induction process, the greater the attraction will be, the dispersion forces. So as you go down this group, what we're saying is the attraction between the fluorine molecules is the weakest, and as you head down, they'll get stronger and stronger and stronger. And it's for that reason, going down this group, boiling point is going to increase. So as you increase size, you increase the number of electrons, and you increase the dispersion forces. Another application of this principle is when you increase the pressure on a gas that is at low temperature, those gases end up liquefying. And the question is, why is that? Well, in the case of, let's say, nitrogen molecules, when you increase the pressure on them, the molecules are forced to come closer together. And so the dispersion forces are going to increase in strength. So decreasing distance, increasing dispersion forces. So increasing pressure is what does that. So the most common question, though, has to do with boiling point. And by the way, I mentioned the halogens, but the same applies not only to the halogens, but to group 18. In group 18, as you go down this group, they're all gases for sure, but as you go down this group, the boiling point of those gases increase, because as we go from helium, which is the smallest, all the way down to radon, which is the largest, there's an increase in size, an increase in number of electrons, and therefore an increase in the dispersion forces. Of the intermolecular forces of attraction, dispersion forces are the least popular as far as questioning. The one that is most popular, the one that is most often asked, has to do with the hydrogen bonding, which is the strongest of all the forces. And what you want to keep in mind for the hydrogen bonding, again, to reiterate, is a question that deals with unusually large or unusually high boiling points. And of course, FON is what you want to remember for the hydrogen bonding. Finally, at the bottom of this page, I have something here about the different types of solids. And the third one, the third category here, the network solid, which was probably covered in your class, I just want to remind you is optional. It's not on the Regents, so we'll just cross that out for now. Let me get a better marker. So there are three types of solids that we're responsible for. First one here would be ionic. Ionic solids consist of ions. A simple example of that would be table salt. Table salt is a solid that's made up of ions. And the ions hold on to each other with strong ionic bonds. All right. Molecular or covalent substance would be ice. Example of that would be ice, consisting of molecules. And the molecules hold on to each other with hydrogen bonds, as we just mentioned a moment ago. But when you compare the attractions between molecules to the attractions between ions, we'd have to say that they are weak in comparison. So these are weak compared to ionic bonds. And when it comes to metals, what's happening here is that in any sample of metal, the reason why the atoms hold on to each other is because you can think of a metal as positive kernels in a sea of mobile electrons. What that means is, remember, metals have loose electrons. And so these loose valence electrons, better said, are shared by all the atoms in a sample of a metal. All right? We think of those electrons as just roaming throughout the sample. All right? And because of that, metals are such good conductors. But the two main points here about ionic and molecular is because of the differences in the strengths of these attractions, the ionic solids, since they have strong ionic bonds, are hard and have high melting points. So when I say a high melting point, compare the melting point of NaCl at 801 degrees Celsius to the melting point of ice, which is 0 degrees Celsius. So that shows you that the ionic bonds are much stronger than the attractions that hold the water molecules together. So molecular solids, in comparison to ionic, are soft and have low melting points. Now, because we see the positive and negative charge here, you're likely to think that ionic bonds, or ionic solids better said, are good conductors. Well, that's not true. While they're in the solid state, these charges aren't free to roam. So in order for an ionic compound to conduct electricity, it has to be in the liquid state or aqueous state to conduct. And that is a very common question. Molecular solids, on the other hand, are poor conductors, and sometimes they're referred to as non-conductors in comparison. And of course, when it comes to metallics, you should remember that they are the best conductors compared to molecular ionic in any state. I wouldn't worry, though, about the hardness or melting point of metallics. When it comes to metallics, any metal will serve as an example for metallic. Finally, then, at the bottom of this page, in very small font, I mentioned the fact that true solids, such as ice and metals and salts, true solids have a definite melting point, a specific temperature at which, when that sample reaches that temperature, it turns from solid to liquid. That temperature does not change throughout. And they also have a specific crystal lattice structure. In other words, a specific three-dimensional arrangement of the particles that make up that solid. Glass doesn't qualify in either case. Glass is not a true solid because it doesn't have a specific melting point. It has a range, it gets softer and softer, and glass does not have a specific pattern in which its particles are arranged. So glass is like a pseudo-solid. All right? Okay, let's do some questions in bonding. This was a pretty big unit, so if you've gotten to this point without stopping, you're really doing good.